Yeah, thanks very much for the introduction, Corinne. Yeah, a warm welcome to today's webinar. Thanks very much for joining us. Start with some very brief introductions. So I'm Rob Shropshire, and I lead the sales and marketing side of Origin. So I won't be doing a lot of the talking today, but most likely will be a point of contact moving forward if you did want to chat with us further. Really pleased to be joined by Tim, who works alongside me, and for the last 10 years or so has been supporting our customers and also delivering training for the solutions that we provide. So a great person to take you through the series of demonstrations that we've got lined up for you today. Quick agenda. As I said, I won't be talking much. I'll spend sort of 4 or 5 minutes just explaining what the Inspire suite actually is in relation to the design for manufacturer workflow, and briefly discussing what we think some of the challenges are, and hopefully how the tools that you'll see today helps to address them. I'll then pass over to Tim, who's got a series of different demos and a couple of different models as well. So hopefully, depending on your industry, you'll see something that's relevant, or at least be able to apply it to what you do in your day to day. After the demo, I'll wrap up briefly. And as Corinne said, that there should be plenty of time for questions. So urge you again, as we go through the session, please put them in the chat, and we'll save them up as we get to the end. So in terms of Origin, as Corinne said, we're a UK-based reseller of Altair solutions. So we do focus specifically on the UK and Ireland, and provide sort of initial training to get users up to speed, and then ongoing support. Our focus is simulation-driven design. In other words, sort of refining, testing, and optimizing designs early on in the design process, but then actually validating the manufacturability of those parts as well through manufacturing simulation. So product-based simulation and sort of manufacturing simulation is, I guess, what we specialize in. And when we talk about implicit modeling, we were thinking about the sort of challenges, and typically the challenges that designers face are to do with more sort of organic or freeform or complex shapes, and also being able to design lattice structures or infills, depending on what you're doing. And one of the reasons this is a challenge is because traditional CAD systems utilize what we call BREP data. In other words, curves and faces where there are sort of quite defined boundary conditions. So when you are doing operations like shelling or offsetting geometry, it often tends to clash, which can cause problems. Traditional CAD systems are great for more sort of prismatic mechanical shapes, but sometimes different tools are better for more organic shapes and lattice structures. So with the Altair Inspire platform, we're able to seamlessly sort of convert and transition between different data types, including polyNURBS and implicit, to easily create these shapes. And that's something that Tim will show you live, and hopefully give you a better understanding of that. Forgetting about the actual design or coming up with the CAD, the other problem tends to be actually simulating these models. So how do we go and run some stress analysis, for example, on what we've designed? And the main reason for that is because of the complex geometry and the ability to actually go and mesh that part. So sometimes that can mean that parts just don't mesh. Sometimes it might mean that meshing takes ages. Or sometimes it might mean that the designer has to do a lot of defeaturing work to get that model to a point where it can mesh. And what that means is that designers don't really have the ability to quickly refine and test different concepts. So with the Altair Inspire platform, the solver is completely meshless. So we don't really care about the complexity of the model. We don't care about the size of the model. And it just means that the designers can just get the software to mesh the part and get results really, really quickly, which lends itself to a more sort of iterative design process. The next challenge then, once we've done the CAD, once we've validated the design, we then need to come and manufacture it. So we need a way really of being able to decide based on what manufacturing technique we're using. We want to be able to simulate the manufacturing process as well. So the Altair Inspire platform also offers that. So when we look at that through the lens of I guess a design workflow, we start with the design. We provide really good sort of file interoperability with other major CAD tools, SolidWorks, CATIA, but also all of your sort of neutral file types. And then we provide geometry tools on top of that, which allow you to create these more complex organic shapes and mix and match and convert different types of CAD data. The platform will then let you validate that design. It might be stress analysis, it might be looking at motion dynamics, it might be looking at airflow, it might be looking at thermal properties. So we've got a toolkit available for that. The software will then allow you to actually optimize that part even further, so it can look at your design space and hit sort of key objectives such as lightweighting, or it might be stiffness, whilst making sure that we're adhering to your manufacturing constraints as well, depending on how it's going to be manufactured. So the ability to optimize the part as well. And then once we think we're at a stage where we're ready, we've done our design, we could then of course simulate the entire manufacturing process to identify common defects and make sure that the method that we're using to produce the part is going to produce the best output. And from a manufacturing perspective, we can simulate the casting process, the injection molding process, the metal forming process, extrusion, and also 3D printing as well. So the chances are, however you're going to manufacture these parts, we've got the right tool for you. So we're not going to have time to go into all of that today, obviously, but hopefully what it shows you is that within one platform, within one license type, you've got the ability to take something all the way from concept design all the way through to manufacture. So that's enough from me. I'll be on towards the end to speak to you again just to wrap up. But in the meantime, Tim, I'll pass over to you.
Cheers, Rob. I'll just share my screen at some point. There we go. Let me know if you're seeing my screen. You seeing anything?
We can see that, yeah.
Yep, can you see my Inspire?
Yes, yeah.
Perfect. Okay, yeah, cheers, Rob. Thanks for the introduction. And again, yeah, thanks everyone for joining us. So over the next sort of 30 minutes, I'll be taking you through some examples of using the implicit modeling functionality within Altair Inspire. As Rob mentioned, it's Inspire can be used as an end-to-end sort of workflow, so we can create initial sketches within the software, and but it can also work alongside or in conjunction with your preferred CAD tool, and going all the way through to, as Rob mentioned, manufacturing verification. So I'm not going to spend too much time going over the Inspire sort of user interface. Just very quickly brushing over it. Model browser on the left hand side, anything we create or import will appear here. Property editor down here on the left, and our history tree as well. So as we design or create something, obviously our history will be built up. The demos are all going to be sort of focused around obviously implicit modeling, and hopefully this will give you a bit of an idea of how maybe implicit modeling can help with your design processes, allowing you to maybe do things that you can't do, or maybe you might struggle with standard geometry. I'm not going to again go into loads and spend loads of time sort of explaining exactly what implicit modeling, how it works and what's going on in the background, but basically it works on sort of mathematical functions are basically used to describe the solid between sort of points in space. And when I say points in space, I sort of mean x, y, z coordinates. A simple example might be if you had a line that was represented on like a 2D XY graph, and that line was at on the 0 level. If I wanted to offset that line, I would just move it to a different point in space. Let's say I wanted to offset it to 2, I'd just move that line to 2. This is sort of what's happening with implicit modeling, but in a 3D space. And it knows where the boundary of that solid is, so it is able to just basically adjust that boundary. So I'm going to just jump into some demos. I'm going to just stop showing my camera while I'm doing these demos, just so I don't take up any bandwidth. But we're in the implicit modeling tab as we are. Really easy to start with. Like, you can just create some just generic primitive sort of shapes. We can create cubes, toruses, pipes, spheres, and we can modify the origin, modify the sizing of these. We can then accept these. And in terms of visualization quality that we can see here, this is going to be set to medium most of the time. I'll set this to medium anyway. But if we increase it to high, the resolution will just increase, and you can see that we've got sort of more sharper edges. So for the purpose of demoing especially, I'll set that to medium. Once we have an implicit body, or even normal geometry, we can then create some lattice structures. So we can create surface lattices, planar lattices, strut-based lattices, stochastic lattices. We can control our fields via points, which we'll show some examples of in a minute. We can convert data to implicit as well. So we can convert data to implicit, whether that be CAD data, BREP data, polynerbs, meshes, and we can also do some modification on our implicit parts. These will be familiar to a lot of people who've used any CAD tools, combining things together, subtracting, intersecting, offsetting. We can actually morph two implicit geometries together, which can create some quite cool shapes. For example, if you merged or morphed a gyroid lattice into a hex-based lattice, you get an interesting sort of shape. But yeah, once you've got an implicit, as I mentioned, you can easily turn this into any sort of lattice, and I'll be going through all of these controls later on, but you can change your unit cell types. So you can see all these here. Obviously these are defined by equations, and I won't be able to go through all of these here, but you can just see all the different cell types that we can use. This is surface lattices. We'll have different ones for planar and strut based. For the first demo, I'm just going to import a model. So this is it's going to be a solid model. It's a head, but it's obviously made up of a number of surfaces. So made up of a number of surfaces, and using traditional, this is what we call BREP CAD data. I think it was originally a parasolid file, but traditional operations, for example, if I wanted to offset this model or shell it out, with traditional CAD, this would be very difficult. Surfaces tend to intersect, surfaces tend to overlap and disappear as we go too far, and that generally breaks a solid. So this, if you wanted to offset this by, let's say 10 mil or something, or inside or outwards, would be near enough impossible with standard geometry. But with implicit, we can do this with ease. So this is just showing you a couple of tools within the implicit tab. First of all, obviously, we can convert any model to implicit. I'll just hit the tick box here, and within a few seconds we'll see this. So you can see we can no longer see the surfaces and the edges, so this is now in implicit mode. Just to do some basic operations like offsetting or shelling, we can use our offset tool. I can click on my part, you can see I can go outwards, I can choose my value. Let's go like a crazy value. You can see interesting sort of shape as we go outwards. But it does it within seconds. It's not going to break. Let's say I'll go inwards, and let's go inwards by 5 mil. Obviously now it's eating away at material. Have lost my ears, and the nose is starting to look a bit pointy. But you can see it's not breaking. It's just doing it very, very easily, and it happens within a matter of, well, not even a second. Let's say I do want to go outwards in this instance. I'll say 5 mil. Maybe I do want to create some sort of shell, so I can tick on a shell. Hit the tick box, and that's what I've done. If I just create a section mode through this, or a section, we can just see what I've created. So really easy to do those sort of operations. If I'm just going to accept, let me just remove or get rid of that one. If we were let's say 3D printing, and we wanted to create some sort of infill shell infill, we might want to use our planer tool. And we can create any sort of infill. In this instance, we've got different types: hexagon, diamond, triangle, rectangle. I'll keep this on hexagon. In terms of my sizing, I can modify the count. Let's just increase that by a cell count, but we can also do it via a value as well. So we can start to see that taking the shape of a head. If I want to modify the origin, so the orientation of these cells, I can just drag this, and let's say I want it to be in the Y direction. I can just transfer that to 90 degrees. So we can modify our fields, and you'll see some more interesting things happening now with modifying and creating the space, the size, and later on in the demos. But let's say I want to shell this out. Again, I want it to be inward to a factor of 5 mil. Again, hit the tick box, and we can create those sort of things. So anyone like working with 3D printing, whether that be metal or plastic, again, these tools can be very useful for. So we can see our shell wall thickness with our infill in that. So that's the first example. The second example I want to show is just this is going to be a fairly quick one, but this is an example of a heat exchanger. So this is a good example for anyone who's sort of like having to think about like thermal properties, the thermal properties of the parts, like heat exchangers, as we've got here, like heat sinks. But anyone who's, as I say, having to think about the thermal properties of parts, implicit modeling is great for that because we can create shapes with larger surface areas, which can lead to sort of improved efficiency. So in this instance, we've got a double gyroid heat exchanger, fluid heat exchanger. So just to very quickly show you how easy that is to create, you could import your geometry as we mentioned from your sort of chosen CAD system, or you can create it within the Inspire software. This is the geometry that I wish to turn into a double gyroid. In this instance, I'd click on my surface lattice, and that's the wrong one. Make sure I click on this part first, and then change this to a double. So I want 2 fluid, hot and cold. Again, we can modify all these sort of things, choose different cell types. So I'm going to keep that as gyroid, modify the density, modify the cell count. Let's say I want that to be, I don't know, 13. And also, if we wanted it to be biased towards one side, so if we let's say I wanted it more biased towards the hot or the cold, I can do that here as well. So I can maybe bias it in this instance by 75-25, and we can do things like that very, very easily. So within a few clicks, you can see that we can start to get to something that looks like this, which is obviously a 2 fluid heat exchanger. So anyone working in thermal, having to think about the thermal properties of the parts, implicit modeling is a great tool for that. So that's just a very quick demo. The next one I want to show is, this is another industry where implicit modeling can be helpful. In this instance, this is a hip joint. So this is sort of the medical industry. This part, there's a couple of things here that's just to mention. This part I have designed myself, so if it does look a bit ropey, I don't design these parts regularly, but I've designed this. It took me about 5 or 10 minutes within Inspire itself. So what you'll see down here on the left hand side is obviously my history of how I've actually built up this model. So what that means is obviously I can go into the history and modify it, etc. But as I've been building this part up, I've been creating some variables as well. So I've got some design variables here. I imagine hip joints aren't all the same size. We might have different sized people, shorter, taller. So I imagine maybe these hip joints do vary in size. So I can quickly change these variables just by my variable manager here. You can see I've just changed the length there of this. Maybe this length here, I want to change that to 30, and this to 70. So really easy to change those directly. So if you are having to update your model, change sizings and things, you can just create your variables and do this within seconds. But what we're looking at here is we're going to go into the implicit modeling tab again and just go through another couple of lattice types. we're going to use the stochastic lattice type, and this can be used to basically sort of mimic bone growth and density with, so what stochastic is, it's like randomly generated points connected by beams. So we're going to use that in a second, but a lot of like medical implants these days are made from titanium, which is a quite an expensive metal, especially if you are printing it. So if you're, as a manufacturer, you can think about, you know, reducing material, but also improving the performance of the implants. You know, if these implants are lighter, maybe they're going to be more comfortable for the end user. And also, you know, we were talking about thermal properties there. When a lot of times you hear complaints about medical implants, that especially in cold conditions, they can feel them. You know, if we've got a larger surface area with less dense material, maybe that'll improve the thermal properties. So that's something else we can start to think about. So obviously this will be good for the manufacturer, less material used, and obviously the main point is it's better for the end user. So we're going to use the stochastic lattice here. So I'm going to click this tool and click on my sort of ball joint or ball there, and with the stochastic lattice we can modify the points and the edges. So our generation method at the moment is just set to uniform random. We can set that to minimum spacing, where it'll always keep a minimum point distance between the points, and we can also use import, for example, a point cloud or something. I'm going to increase my point count to 5,000, and you can see obviously that density change in the preview. If we go then onto edges, again we've got different generation methods, Valance or Delaney, and we can again modify the valence. So in this instance it will just be the connection points, connection beams between points. If I decrease that to 2, increase that to 4, there's going to be more connection points between the randomly generated points. Once I'm happy with that, I can hit the tick box, and you can see what I've created. We can then go on to modify it further. In this instance, I'm going to keep it as the default solid and regular, and I might want to just increase or decrease my strut or beam diameter. So let's just change that to, I don't know, 1.5. Again, once we've done this, we can then decide what we want to do with the outer body. You know, do we want to create a shell around this? Do we want to combine it with other geometry? So in this instance, I might want to combine it with some other geometry that I've created. So I click the combine tool, choose what I wish to combine it with. This transition here where it says sharp at the moment, what that is the transition, as I say, between the points where the lattice meets the object. You can set that set to sharp. If I set that to fillet, we'll just see it more rounded off there, and obviously I can give it a value. So that's just a quick example of stochastic lattices within Altair Inspire and how those can be potentially used. Next, I'm going to just quickly create a strut-based lattice on this part. Just want to show you a couple of other features and how we can control these lattice features. So if I put it on this part, again, I'm not going to go through all the different cell types that we can use, but hopefully you can see a couple of them here. Let's just change it just so you can see those change. So I'm going to set that to, in this instance, diamond. Down here, we can again control the coordinate system. We can also conform lattices to surfaces. So if you have got a surface or you want to conform a lattice to, that's something that we can be doing in the software. I am again just sort of scratching the surface of what the capabilities of what we can do sort of within implicit modeling. But in terms of sizing, I can increase or decrease the density of the cell count. But we might also want to control the sort of the sizing of these struts via a gradient, and that can be done using the field tool. So we can apply a field. I can say create field. At the moment, the field, the driving object of the field is being driven by this plane, which is in the z-axis. I want it to be in the y-axis, so I'm going to just change that with my global y in my model tree. We've got the input range, minimum distance to maximum distance. I am happy with that, sort of start to the end of my part in this instance. And then we can modify our strut thicknesses. So let's say I want it to be the smallest one to be 2 and the largest one to be 8 or 7. Obviously, you can choose whatever values you wish. And hopefully there we can see now we've got a gradient from it going from thinner to sort of thicker. So that's just another thing that we can do. In the next example, we'll show how you can do that as well with stress-based results, which will come in a second. But in terms of actually controlling things, you know, like walls and stuff and shells and having open faces, that can all be controlled as well through the options when we shell things out and combine things with other geometry. Obviously, this part now we've got some implicit tools. We can still modify our design variables. So, like, you know, here, if I did want to change that to 250, you know, increase the length at this point, that can be done. So you can see now this is just obviously a lot longer. Doesn't look great down there, but we can change our designs via our variable manager at this point. So that's the third demo. The fourth demo that I'm going to show is going to be how we can use sort of stress-based results in conjunction with our implicit modeling. What's important to note, I think, is currently we've just probably looked at a few examples that have probably been more beneficial to sort of 3D printing. I think it's important to note that implicit modeling doesn't just have to be used for 3D printing. It can be used for any other manufacturing process, whether that be machine parts, cast parts, injection molded parts. Obviously, it's all about understanding how those parts need to be made, but you can obviously control what you're creating as well. So this part is obviously an excavator arm. Probably wouldn't want to 3D print this unless it was very small. In this instance, it's, you know, more likely to be like these parts probably be like cast or something. So I'm going to set up a stress analysis in a minute, but there is another cool feature, you know, within Altair Inspire. We do have motion dynamics. I'll just, you know, sort of going off on a tangent here, but this will take about 30 seconds to a minute. I'll just set up a quick motion dynamics just because it's quite a cool feature within the software. So in this instance, I'm just going to ground this part here. That's going to be ground. If I click my joints tool, we can click on automatically find, and we can find all these joints. I'm going to set them all as active. We can then set up some actuators, some motors. I'm going to set up a motor on this point here. I'm going to reverse it, and I'm going to say, rather than speed, it's going to be controlled just by angle. And I'll set that. We can set up, as I said, some actuators if I want. Box select those. And if I want to modify the values, I can do up here. So really, really easy to like to just one, create stuff, but two, modify stuff. So you can see I'm setting up something literally probably taking me under a minute to set something up. And if I click on my analyze part, let's just fix that if it hasn't got a mass. And we can show some sort of motion. So that's just, I just want to just quickly show you that, but we can show motion. We can go further with that. Obviously, we can analyze the motion and understand where the stresses are and stuff using motion dynamics. But that's just something that's, you know, in Inspire that's quite cool. But went off on a little bit of a tangent there. Coming back to this model using stress-based results to drive the implicit fields. First of all, I'm going to go into my structural tab and just set up. I'm going to set up a very straightforward, simple analysis. I'm going to select on these, not that one, these pieces, and I'm going to just ignore these for structure analysis. There we go. I want that one. So I'm going to ignore all these for structure analysis just for the purpose of simplification. So I'm going to ignore those. And then I'm going to create some joints. So again, similar to the motion dynamics, but this time I'm going to have these as sort of locked, just because I want it sort of, this is the position it's locked in, this is the forces that I'm interested in this locked position that it's in at the moment. I don't have to worry about those because obviously I've ignored those parts. Then in terms of my loads and my forces, first of all, I'm going to set up a fixed support. So I'm going to just say it's fixed on this face here. So that's sort of fixed at that point. And then in terms of forces, I'm just going to apply a force evenly distributed along there, let's say in the Y direction. So it's going down we'll say the -y direction, make sure it's going in the right direction, and I'm just going to type in a random value. So just setting up something a bit, you know, random, but you know, you'd be a bit more precise if you were doing this for real. Once we've got that set up, we can actually then analyze it. And as Rob was mentioning earlier, within Inspire, we do have two solvers. There's what we call an OptiStruct solver, which is more traditional, sort of FE based. You would create a mesh, and then so it would first create the mesh, and then it would run the analysis on the mesh. But we also have the SimSolid, the meshless solver. This is obviously a great tool for working with large assemblies, not having to simplify your parts, and it's really, really quick. So you'll see in a second, I'm going to literally press the analyze tool. I'm not going to mess around with my setup here. I might turn on gravity, for example, but we can play around here. For the speed, I'm just going to do fat for stiffness, but it's going to, even if I did stress, it'd run in 10 seconds. I'll click the run tool, and you'll see probably within about 2 or 3 seconds, we've got results. So literally, we've got results within seconds. I can then analyze these results if I want to. I'm not too fussed about the results at the moment. You know, this isn't a structural webinar. This is mainly for implicit modeling. So what the things that I'm interested in this instance is the stress on this model. So I'm interested in potentially using my implicit modeling tools to maybe reduce some of the weight on this sort of large arm, this piece here. So I can see I can always over exaggerate certain areas so they can, you know, highlight and stuff using these values, but I'm not going to go into too much detail there. But I can clearly see that if I use my call outs, there's more stress down here, you know, less stress in this area. So using our call outs, we can literally just put a couple of points, you know, values around this part, like such. So I can just put some call outs, put a few on there. Again, depending on the part, you might use the area that you wish to, you know, use your implicit modeling on. You might use less, you might use more. Once I've got that, I can then take these values. I'm just going to make this a little bit bigger. And I'm not interested in the factor of safety, so I'm just going to turn that off. I'm not interested in displacement. So von Mises stress I am interested in, but also the position. So the X, Y, Z positions, obviously this is the positions in space that will allow me to create a point cloud. So this is the information that I'm interested in. I would basically take this, I could just copy Control A, copy these, Control C, and put them into an Excel document. This would look something like this. So we've got our X, Y, Z coordinates, and we've got our stress results. So then we're going to use these to see if we can obviously, you know, reduce some mass of this part. This is quite a large part, so if we can reduce some mass, you know, that might be beneficial. We can see here that this part actually weighs 6,000 kilograms, so it's quite a large part. So I'm going to go to just this arm. I'm going to open this arm up, and I've actually chopped it in half as well, because obviously if we were going to do this, we might do it on both sides and mirror it. And this is the area that I wish to create some sort of like lattice structure. So going back into my implicit modeling tab, first thing I'm going to create a point cloud, and that was the Excel file. So that's my Excel file there. We can see your points appear on the model. Make sure you're happy with them, hit the tick box. Then I'm going to create a planar lattice on this area that I'm interested in. And the sizing, or we can control, again, we can control both of these via fields, but what I'm going to try and control by a field, or what I am going to control by a field, is the thickness. So where there's more stress, I want it to be thicker. Where there's less stress, I want it to be thinner. So we do this by clicking on this tool to create a field. And then this time the driving object rather than an axis is going to be my point cloud. My minimum distance and maximum distance in this instance is going to be my minimum value, stress value, and maximum stress value. I think mine was something like 6 megapascals and maybe like, I can't actually remember, but about 38. So I'm going to put those there. And then we can again define our thicknesses. So maybe I want my minimum strut value to be 7 and my maximum to be, I don't know, 30. So what we can see here is where the highest stress areas are. We're going to have thicker struts, or thicker hexagon lattices, points and cells, and then where there's less stress, we're going to have thinner. So that's another cool feature within Altair Inspire. You've been able to drive those implicit values via the fields, but they've come from obviously our stress values. So I can hit the tick box. I can, let's combine this with my outer body. I'm not interested in it being sharp. Again, the resolution obviously a little bit low there. Let's just increase that while I combine it. And hit the tick box. And then I can weigh this part. So I just want to quickly check the mass. I would mirror it and everything. So we can see just under 2,500 kilograms. So you can see by doing something like that, we would want to obviously then go on and verify this. So we could then use our SimSolid solver to actually verify the results and make sure it still does take the loads that it needs to. But potentially saving 1,000 kilograms per part, that might be quite a big saving. Again, a lot of companies are looking to how they can go greener, how they can save on material. One way is obviously reducing material costs. One final thing just to mention about point clouds is also you can locally modify your implicit parts via point clouds. So if I create a shape, I'm just going to make that quality to the medium. In this instance, I'm going to create a cuboid, just a random shape. But this can be used on any implicit part. If I create a point cloud and I put the point, let's say here, I'm going to use the cuboid as a field, and then I can start to modify these values. So I'm going to just increase the radius of sort of like effect. So if I this will be, you can see where my sort of effect is. So that's just a spherical radius. I can then play around with the value, so I can go negative or into the part. You can see it's quite noisy, so it's just affecting this area, but I can use this fall off to start to smooth that area out. And this can be used again on any sort of lattice or any area. So if you want to locally modify an area, you can use points to actually do that as well. So that's another cool feature within points. And you can see I've just locally modified that area. So that's just a few demonstrations, hopefully giving you a bit of a flavour for how implicit modelling can be used to sort of aid in your design processes. Inspire as a general tool from start to finish, there's a lot more manufacturing tools added on, like Rob's mentioned, that we can show you. So if you are interested in any of those or any of the other things that you've seen within any of these tabs that we haven't sort of covered, please do get in touch, because we can show you those in more detail. But obviously we've only got a certain amount of time. So that's the sort of demonstration finished. Those are the 4 demos that I wish to show. So I think I'll pass you back to Rob now.
I can probably